brings us to our very last part of this formula. So if they really want to be a pain, we know the formula for water potential, and we said that water potential was equal to two things. It was equal to solute potential plus pressure potential. They will tell you on the formula sheet all of this information. One thing they'll tell you about pressure potential in an open container, I don't know if I mentioned this, in an open container, the pressure potential, we consider it to be 0. Even though there's gravity. We only count pressure potential if there's like physical pressure, like a plunger or something. So in an open container, the pressure potential would be 0. The solute potential, they might make you calculate, which is a complicated looking formula, but it's really not very hard. Now, notice it's always negative. For pure water, I mentioned this, for pure water, it's 0. But the more solute you add, the more negative the solute potential is going to get. So let me explain the parts of the formula, and then we'll do a couple of practice problems and we'll be done. So ionization constant is I. The ionization constant, they're going to tell you that for sucrose, which is what we used in the lab, is 1. So that's just going to be 1. Ionization constant is a measure of how many ions something breaks into when you add it to water, when it ionizes. If they give you sucrose, if they give you glucose, if they just say sugar solution, all of these are just going to be 1 because they're not ionic, they're covalent, which means they don't break into multiple ions. One sugar molecule stays one sugar molecule. And they tell you that on the formula sheet. My guess is that they would always give you, at least any time on the AP exam I've ever seen this formula, it was always glucose or sucrose that they gave as the solution. But if they did give you something ionic, then the number of ions it splits into would be your ionization constant. So for sodium chloride, for example, it splits into 1 sodium and 1 chloride, I would be 2. What would it be for calcium chloride, CaCl2? How many would that split into? 3. Like you'd literally count 2 chlorides, 1 calcium, it would be 3. So the ionization constant is the number of ions that a compound breaks into. My guess is that they would give you one of these things, which are not ionic, so it's just 1. You don't even have to worry about that number. It's 1, so it's not going to change your answer in any way. But if they did give you an ionic compound, you would have to multiply out and figure out how many ions were in the compound. C is the molarity of the solution. R is a constant. It's called the pressure constant. It's 0.0831. You may recognize a similar constant we used in chemistry for gas laws. Except we weren't using bars. We were using ATM, so it was 0.0821. But it's a very similar constant. And then the temperature has to be in Kelvin, so you have to add 273. All of this information, all of this, is on the formula sheet. So you don't have to memorize it. You just have to know how to plug it in. So I put a sample problem here as a walkthrough just to show you how it all sort of fits together. So it's a 1.0 molar sugar solution, sugar is important, at 22 degrees Celsius. And they want you to calculate the solute potential. So it's negative ICRT. So negative sugar, I is going to be 1. C, concentration, is your molarity, so that's 1.0. The gas constant, or the pressure constant, R, is going to be 0.0831. And the temperature is 22, and they remind you to change it to Kelvin, and they tell you the formula to do that. You add 273, it's going to be 295. Now, I color-coded all the units here just to show you everything cancels, and you end up with bars. So remember how in the beginning I told you your units for this will always be bars. Notice what happens when you plug this in. Kelvin cancels. Liters cancels. Moles cancels. Your answer ends up being in bars. So if you just remember to write your answer with the units of bars, you don't have to worry about figuring out your units. It will always cancel out to bars. Also notice it's always negative. So negative 24.5 bars, they will always tell you where they want you to round as well. So it's really just a matter of plugging the numbers into the formula and then solving. The biggest mistake, the biggest deduction on the test for this is people forget the negative sign. It's always negative, always. It is never, ever a positive number. The formula is negative ICRT. So don't forget your negative sign when you solve it, because that's the biggest mistake. I would say 20% of people forget. They put the answer and they leave off the negative sign. And it should be negative. So keep that in mind. So these are just 3 practice problems to try out with the formula real quick, and we'll go over them together, and then we'll wrap it. All right, for the first one, so the solute is sucrose, so what's I? I is just 1. C is our molarity. R is a constant, 0.0831. T is our temperature, 22 degrees, plus add 273, so 295. When you work that out, you should get negative 2.5 bars for the first one. The second one, the solute is sodium chloride, so what's I? So I is 2, so this is going to be 2. Molarity is 0.5. The constant is always the same. And at 0 degrees Celsius, that's 273 Kelvin. So this one comes out to negative 22.7 bars. The last question, they said, okay, they want to know what the water potential is. The water potential is the solute plus the pressure. They want you to use the solute from question 2 that we just did. So negative 22.7 plus the pressure is 8.5 bars, which would make the final water potential negative 14.2 bars. All right. So that brings us to the very last thing. So this is how you would do basic solute potential problems. We've learned the water potential formula. We've learned how to calculate solute potential if that's not given to you, to then plug into that formula. The very last thing is this. Let's say, like what happened in your lab, I don't tell you what the molarity is. In other words, this variable is not given. They said the temperature was 27 degrees Celsius. They give a whole situation that these are zucchini cubes that were put into different concentrations. Some of them gained weight, some of them lost weight, and they want you to graph it. And if I graph this, I can see that at distilled water, which is 0, it gained 20. At 0.2, it gains 10. At 0.4, it lost 3. This is not going to end up being beautiful, but at 0.6, it's at negative 17, so it's about here. At 0.8, it's 25. And at 1.0, it's down at 30, which sort of goes off my graph that I made. But I can pretty much connect this. So this is sort of a graph like what you would get for your potatoes, something like this. This is based on sucrose, and this is supposedly zucchini. They want you to calculate the solute potential for the zucchini, and they said the temperature in the room was 27 degrees. So it tells you that it was sucrose, so I is just going to be 1. We'll come back to C. R is 0.0831, and our temperature was 27 degrees Celsius. If we add 273, that gives us, I believe it's 290, oh, it's 300, yeah. The one thing that they didn't provide you with was the molarity, because they want you to get the molarity from your graph. So if we go all the way back to one of the first things we talked about, in your potatoes, the same thing is true. If we figure out where it crosses the x-axis, that would be the molarity of the actual zucchini, or in our case, the actual potatoes. That is our best estimate of what solution would be isotonic to our potatoes. So if I estimate, let's just say that it crosses the graph at around let's say 0.36, then that would mean that the molarity that I think is in the actual zucchini is 0.36 molar. That's what I would plug in for C. So rather than them giving you the molarity, you get it from your graph. Once you graph, it's wherever it crosses the x-axis. That's our best estimate of the molarity of, in your case, it's going to be the potatoes. And now you just plug in all of your numbers. If you do this and round it to 1 decimal place, it ends up being, it comes out to like negative 8.97 bars. So basically that would be around 9.0 bars. That would be the solute potential for, in this case, the zucchini. They gave you a pressure, just to wrap it up. Since the water potential is the solute plus the pressure, they're giving you a pressure inside the zucchini, in which case you would basically do this. So you take your negative 9.0 plus your pressure, which they're telling you is 2.3. And so the final water potential in this case for the zucchini would be negative 6.7 bars. Make sure that is negative. So that would be your final water potential. So that's how you'll do part 3 of the lab. They'll ask you have to figure out which solution is which by the gaining and losing of weight, graph your data, where it crosses the X, that's going to give you your molarity of the potatoes in your case. That's C. I provide you in the lab with a temperature. It's not 27. I believe it's 22 or 23, which is about what this room should be.